Welcome to Logarithmic Functions. Today we will be looking at the connections between the exponential functions in Lesson 1 and the logarithmic function today. First of all, the logarithmic function is the inverse of the exponential function. You will find y equals the log base a of x if and only if x equals a to the y power. An example that we could use would be one like log base 2 of 8 equals 3 because 2 to the third power is equal to 8. The logarithm and the exponential will always keep the same base, here base 2. The difference is, in the exponential, the power finds you the value. The logarithm, being the inverse of the exponential, takes the value and finds you the power on the base to get that value. You will notice your calculator only has one log button. That's because your calculator is in base 10 only. Regardless of the base, all logarithmic functions have the same general shape. That would be one such as this one here. You will notice it is the inverse of the exponential function. So from our previous chapters, when we dealt with inverses, we know the inverse graphs should be a reflection over the line y equals x, which the logarithmic function is. The domain of the logarithm comes from the range of the exponential, which is 0 to infinity. The range of the log function is the domain of the exponential, which is negative infinity to positive infinity. Instead of having a y-intercept, the log function has an x-intercept at 1, 0. It is still increasing, however. Rather than a horizontal asymptote, which our exponential function has, the logarithmic function has a vertical asymptote at x is equal to 0. And another difference is, rather than being concave up, the logarithmic function is concave down. We will still use our transformations just the same as we did for all our other functions. The graph of y is equal to 4 plus log base 2 of x plus 2 will have two transformations occurring. One will make it move left. The other will make it move up. And so when I put these together, I will find that my asymptote, which is normally at x is equal to 0, will move left 2. So now it is at x is equal to negative 2. I will find that my x-intercept, which is normally at 1, 0, will also move left 2, and also up 4, which will put it at negative 1, 4. And my shape will be the exact same, and I will follow my vertical asymptote, and I have a slow increasing function concave down. The log base e of x is the exact same as the natural logarithmic function. This is also a button on your graphing calculator, and it will be the inverse of our Euler's constant base. Thus, the natural log function will follow the exact same shape and exact same graph as the common log function. Some of the properties of logarithms are as follows. These are the basic ones. We'll learn more about the properties in the next section, but for now, we should know that the log base a of 1 is equal to 0. Log base a of a is equal to 1. Log base a of a to the x will equal x. A to the log base a of x is equal to x. And if the log base a of x equals the log base a of y, we know that x is equal to y. Now, why do some of these work? Well, first of all, in property 1, we're asking ourselves, any base to the 0 power will equal 1. This is an exponent rule we learned in Algebra 2 and will still hold today. In property 2, it's saying that a base a to the first power will always equal base a. Properties 3 and 4 use the inverse idea. We're basically composing inverse functions, and we know what happens when we compose inverse functions. We end up with what we started with. So in property 3, I'm composing the log of a to the x. See how the bases are indeed the same here and here? Therefore, they're inverse functions. This is the exponential, this is the logarithmic. They're going to undo each other, and we will be left with just our x. Likewise, in property 4, we're just going in the opposite direction. I'm taking base a, and I'm raising it to the log base a of x power. Again, the exponential cancels out with the logarithmic, and we're left with what we started with, which was x. And again, it does not matter what base logarithm you're working in, the properties will still be the same. So now let's take a look at some examples where we're actually finding values of logarithmic functions or of expressions involving logarithmic functions. In this one, we're asking ourselves log base 2 of 32. Well, I know from previous studies that 32 can be rewritten as 2 to the 5th power. So really, log base 2 of 32 is the same as asking log base 2 of 2 to the 5th. Now the nice thing here is I notice my bases are the same. In the case where base of a log part and the base of an exponential part are the same, that means they're inverses, they're going to undo each other, and we will simply be left with our value, which is right up here, and so y is equal to 5. This is another one of our properties. We now know that when we take the log of any base of 1, that's really asking us what power of 3 gets us 1. Well, again, any base to the 0 power will equal 1. Therefore, y here is equal to 0. So go ahead and try to evaluate log base 10 of 1 over 100, keeping in mind your exponent rules for 1/100th. And so you'll see that when I rewrite 1 over 100 in its exponential form, which is 10 to the negative 2 power, I now have common bases. My log and my exponential are the same base. They're inverses. They undo each other. What I started with up here is what I end with as my value. Now let's take a look at an example. The amount you remember after t months can be modeled by this logarithmic function. F of t is equal to 75 minus 6 times the natural log of the quantity t plus 1. And so I'm going to ask you a few questions about this model. First of all, what was the average score on the initial test? And that is correct. Placing 0 in for t, we will find that the natural log of 1 is 0. Negative 6 times 0 is also 0. 75 minus 0 gives me my initial score of 75. So now, go ahead and use your calculators to try to find the average score after 2 months and after 6 months. Hopefully you found the average score after 2 months to be 68.4 and the average score after 6 months to be 63.3. That is all for logarithmic functions for now. Next lesson will be more on the properties and using properties to simplify logarithmic expressions and to solve logarithmic equations.